Okay, notes 2, chi-square test for homogeneity. So it says chi-squared versus 2 proportion z-test. What's the difference? So the 2 proportion z-test allows us to compare the proportions of successes between 2 populations, versus a chi-square test for homogeneity will allow us to compare the proportion of successes over several populations. So looking at the example, it says, after turning the age of 18, do males and females differ in their living arrangements with their parents? We select 2 separate random samples of 200 males and 150 females who are between the ages of 18 to 20 to determine where they live. The results are on the table to the right. So this is our observed data, okay, because this is what happened when they ran the simulation. In order to create hypotheses, what we're going to do that's different than the goodness of fit is that our null and alternative hypothesis are no longer talking about the proportion. Instead, our null hypothesis is mentioning if there is no difference, and our alternative is saying that there is a difference. So if we were to write that in context of our problem, the null hypothesis would be there is no difference in the distribution of living arrangements for males and females. Versus the alternative is that there is a difference in the distribution of living arrangements for males and females. Okay, notice for the alternative in the null hypothesis is that for the null, we're saying there is no difference in the distribution, and then we write context. And then the alternative, we say there is a difference in the distribution, then we write context. Okay, then it moves on to expected counts. To find expected counts, we're assuming the null hypothesis is true, stating that there is no difference in the distribution. We would expect this proportion to be the same across all living situations. However, this does not mean the expected counts will be the same. In order to find expected counts, since we're dealing with a two-way table, is we are going to take the row total, multiply it by the column total, and divide the whole thing by the table total. Okay, much different than expected counts for goodness of fit, because we took the proportion and multiplied it by the total to find the expected counts. But since we're dealing with a two-way table, so more than one categorical variable, we'll use this formula instead. Okay, so using that formula to fill in the table here, I'm first going to start with this box right here. So it says female, and then you're living with parents. So remember, it's the row total. So for female, that row total is 150 times the column total. So with parents, that column would be 121, all divided by the total, which is 350. So it would be 150 times 121 divided by 350. I can put that in my calculator. And I get 51.86. Okay. And I'm color coding so you can see where those numbers are coming from. So let's go ahead and look at the next example, males who live in the dorm. So here's the row total for males, and here's the column total for those who live in the dorm. So that would be 200 times 173, all divided by 350. And if you were to put that on Desmos, you would get 98.86. Okay, so you're going to do the same thing to complete the table. And if you want to pause the video and try to fill it in on your own, that would be the best strategy. If not, I'm just going to fill in the answers now. So 24, 74.14, 69.14, and then 32. Okay, then that takes us to conditions. Notice that the conditions are the same, exactly like goodness of fit. We're still seeing if it's a random sample or a random assignment. We're still using the table total or the total overall to confirm independence by checking the 10% condition. And then for large counts, we state that all expected counts must be greater than 5. So if we look at our expected counts table, notice that all those numbers are bigger than 5, so that would be a condition that is met. Okay, then moving on to chi-squared statistic, we already used that formula before, and then we even confirmed that formula even further when we did the M&M lab. Then that takes us to degrees of freedom. So remember, for goodness of fit, it was number of categories minus 1. Well, since we have multiple categories here, instead of looking at that way, we're going to say that this is the number of rows minus 1 times the number of columns minus 1. Okay, so for rows, that was male and female, so 2 minus 1 is 1. And for columns, those were the 3 types of living arrangements, and there was 3 of them, so we subtract 1 is 2, so 1 times 2 is 2. Okay, then it talks on about the p-value, but we already know how to find that on Desmos, and I will remind you in just a moment. And then that brings us back to our example, and notice that that example is exactly the same as the one that we were doing in the beginning. It does give you your observed counts, and for this function on Desmos, you only need the observed counts. You will not need to write down any of the expected counts or solve those expected counts by hand. I will show you how to find all that information on Desmos. So it says, does the data suggest at a 5% significance level that males and females differ in their living arrangements? Okay, so let's start with C, communicate. Okay, so communicate, we're still putting our hypotheses. So the null hypothesis is that there is no difference. And since we already wrote this in the notes, I'm just going to go ... Please don't do that on the test. And then alternative is that there is a difference. Okay, and then we write down our expected counts table. So that's the table that we filled in all the boxes above. Okay, so we have living with parents, we have an apartment, and then we have the dorm. And then we have female and male. And then I'm just plugging in the numbers that we already found, and I'm going to show you how to find these numbers on Desmos, which means you do not need to calculate this every single time. Honestly, the only time you're going to end up using that formula is on a multiple choice test. Sorry, multiple choice question. Okay, then from here, I'm going to go to my conditions. Okay, for random, if we look back at the problem, it says that we have 2 random samples. For independence, we're using the 10% condition. So we take the table total, which is 350, and we state that this is less than or equal to 10% of all people 18 to 20. That's important because we weren't just looking at all people. We were only looking at people in that age group. And then for the last one, large counts, we state that all expected counts are greater than 5. Okay. Then that brings us to calculate. So we first write the name of our inference. So this is a chi-squared test for homogeneity. Okay. And then in order to calculate this, on Desmos, I'm going to go to add an inference, Okay, and then notice how we don't see homogeneity here, but we see chi-squared test for independence. We're going to click on the one for independence because what we're going to notice later on is that we use this same formula for homogeneity, independence, and association. So we're going to click that one. And then right here where it says group 1, group A, we're going to type in our observed values. So our observed counts. Do not put in expected counts. So I'm going to type in 61, 60, and then 29, 27, and then 60 and 113. Hit create tests. And if I click on this drop down right here, notice that all these numbers that are in parentheses on the table are actually our expected counts. So that's where we would find the expected counts to form the table and the communicate. Then I go down to significance test, and here are all my answers. Okay, so I have chi-squared is equal to 9.365. P-value is equal to 0.009. Degrees of freedom is equal to 2. And then alpha from my problem is 0.05. So then for my conclusion, I'm going to compare my p-value to alpha, and I notice that my p-value is smaller than alpha, so I'm going to reject the null hypothesis. Okay, since I am running out of room here, I'm just going to go ahead and erase this table so I can write my conclusion. So for my conclusion, I'm going to say that since our p-value equal to 0.009 is less than alpha equal to 0.05, we reject the null hypothesis, which means we have convincing evidence that there is a difference in the distribution of living arrangements among 18 to 20-year-old males and females.